Hello everyone, welcome to the course Renewable Energy Technology, and this is the Hydropower series. This series is divided into two parts. The first part is on micro and small hydropower, which will be taken by me, and the second series will be on large hydropower, which will be delivered by Mr. Babak. The first series on micro and small hydropower will be divided into three subsections. The first section will talk about more on story and the classifications and the potential of hydropower, and the second series will be basically on the micro hydro component design and guidelines, and the third series will be on flow curve, head loss, and the power estimations, and also there will be some tips on survey. I will start with a brief history on hydropower. The hydropower history started with water wheels, and that was, if you look at the historical background, in China was the pioneer in water power, and it started from 2002 BC to 980. The world's first factory-based hydropower was installed in England in 1771. The water wheels was used in the past for the end users in the rural areas, and that is even continued today. If you look at the rural areas of developing countries, so this is still not a history in many developing countries. If you look at the water turbine, the first half 19th century is key in development of the hydro technology. In 1849, British American engineers James Francis developed the Francis turbine, and in 1870, American inventor Lester Alan Pelton developed the Pelton turbine, and soon in 1993, Australian professor Victor Kaplan developed Kaplan turbine. And hydroelectric power, if you look at hydroelectricity power, the world's first hydroelectric project was built in 1878 in England, and the first hydropower plant that is serving to the consumer, private and the commercial consumer, was first built in 1882 in USA. Here you can see some of the slides showing the historical development of hydropower. One is showing the central station DC current hydro in USA, built in 1882. Here is another example of historic power stations that was built in Sweden in 1993. And this is the Pelton turbine that was installed in Norway in 1917. And this is another example of Francis turbine spiral casing assembly that is installed in Sweden in 1929. And this one is the example with Kaplan turbine installed in 1931 in Sweden. Now I would like to start the discussion with hydropower classifications, and the hydropower can be classified based on the size, based on the reservoir system, and also based upon the head. Based on the size, basically there is no consensus about the definition regarding the site categories. However, the mostly used classification is as follows. If the powerhouse is less than 5 kilowatt, we say pico hydro. If the powerhouse is 5 to 100 kilowatt, then we will say micro hydro, and then 100 to 1 megawatt, we say it's as a mini hydro, and 1 megawatt to 10 megawatt small hydro, 10 megawatt to 100 megawatt as a medium hydro, and above the 100 megawatt we say it's a large hydropower project. Based on the head, if the head is less than 3 meters, we say is ultra low head. If the head is 3 to 40 meters, we'll say low head, and 40 to 75 meters, we say medium head, and if the head is above 75 meters, then we say it's as a high head project. If you look at the low head, this kind of projects is mainly installed in the flat land, and usually Kaplan turbines are used and most suitable for this kind of projects. But if you want to install a small hydro projects or micro hydro projects, then in that case cross flow turbine will be suited for the low head. And these projects basically have no storage or daily pond days, and relatively this kind of project have high production cost. In the medium head projects are mostly suited in the hilly and mountainous regions, and Kaplan and Francis turbine are mostly suitable for this kind of head. And if you want to install a small hydro projects, then or in the micro hydro projects, maybe the cross flow or Pelton turbines are more useful, and they might have daily or weekly storage, and these projects are relatively moderate in the production cost. And if you go to the mountainous regions which have a high head, and in such cases Francis and Pelton turbines are mostly used, and especially they might have seasonal or annual storage tank, and relatively the production cost with the high head projects are always low. Based on the storage capacity, the projects can be divided into run-of-river type projects, storage type projects, or reservoir type projects, and pump storage type project. Run-of-river type projects, you can see here, this represents a run-of-river type projects, and in these projects electricity production is available through the whatever water flow available in the river, and maybe in such projects there might be short-term storage, hourly storage, or daily or weekly storage. And normally this kind of projects acts as a base load power plants. And in the reservoir projects are mainly built to reduce the dependence on the variability of inflow. Reservoirs are often situated in the river valleys, and also there are some natural lakes available in the mountainous regions, and they can be utilized as a natural reservoir in the case of reservoir projects. And while designing this kind of reservoir projects, we might need to think of the upstream side as well as downstream side, and also sometimes when building a large reservoir projects, we need to have some agreement with the neighboring states or neighboring countries. And also this kind of projects demands detailed environmental impact assessments, since this kind of projects can have more environmental impacts compared to the run-of type river projects. Pump storage type. In the pump storage type projects, we have two storage. One is in the upper reservoir, and second one is the lower reservoir. And water is pumped into the upper storage basin during the off-peak hour with the surplus electricity, and electricity is generated in the peak hour, so that we can utilize this storage water in the peak period and again generate the electricity. So this will give you one kind of energy storage system, and it is an efficient energy storage system for the water power. Now I would like to talk about the global hydropower potential. This map shows you the potential of hydropower in the various regions, and it has been studied in 2005 and showed that there is a potential of 14,368 terawatt hour per year in the world, and most of the power is generated in Asia. The high potential is there in Asia, followed by the Latin America. But however, if you look at the share of the harnessed power is very less at the moment. So if you look at Africa, only 5% of the potential power have been harnessed so far. I want to show you the recent installed capacity in the world. Here you can see the Asia has an installed capacity of 375 gigawatt. East Asia has installed capacity of 280 gigawatt. Europe have 227 gigawatt. North America 164 gigawatt, and the lowest one is with Africa with 13.6 gigawatt installed capacity. Now I would like to give you the short description about the hydropower components. Basically, hydropower components can be divided into weir and intake, gravel trap, headrest canal, descending basin, forebay tank, penstock pipe, powerhouse and tail race. If you look at this drawing here, the weir is constructed in the river to divert the water in the intake, and intake is basically the inlet point for the water that comes to the powerhouse. And normally these intakes are coupled with gravel trap, and in the gravel trap you try to settle down the big particles, sand particles coming in with the water, and then the water is carried to the powerhouse through head race channel up to the descending basin or forward tank. And descending basin is mainly designed for settling down the silt particle that are coming with the water, and then the water is passed through the powerhouse to the turbine, basically through the penstock pipe, and the powerhouse basically house turbine, generator and other control equipments in the powerhouse. And tail is basically again takes back the water to the river. We will discuss this more in the next sessions. So, this is the end of the lecture series 1.1. So, in the next session we will discuss more about micro hydro component design guidelines. Thank you for listening.